So let's review the Lexer implementation and see how it actually implements these rules. So let's scroll to the first part of it, the expression rule, and the actual method name is expression rule right here. So let's begin. So first we check whether we are at the end of the token stream. Remember, token stream represents all the tokens. So then we check whether there is a left-hand side. So we basically say that this is called left. So right here, I'll just try to push up a little bit and show you the correspondence. So basically this first part of this expression is going to be called left over here, and it's handled by term rule. Okay, so this term is checked by the call into the method term rule. Now notice that each of these rules returns the node. So if the term rule succeeds, this becomes an actual node. Then we move forward and we check whether it's the end. If this is the end, we return this part only and say we're all done, right? So we just generate this and we return it. But if it's not at the end of the stream, then we continue and we check for plus and for minus. So clearly this check for plus and minus happens next. And right here we have this check that allows us to see whether this was the case. And if it's a plus or minus, then what we do, we say that what we need to handle here is a fork, basically plus or minus, like this, right? So plus or minus becomes a fork node. And this left node we already have. The left node was already constructed by the term rule. And so the next step that happens here is that we construct the fork, and then once again we call the term rule and we call this node the right node. And so here this term rule is applied the second time. We call term rule, and again we generate the right node. So we get the left node by calling term rule like this. We if we are at the end of the tree, we stop right here and we say we're all done, or we check for plus or minus, and then we generate the fork right here. This is the fork. So we just simply create fork that we create right here. We create this fork node. Okay, so that looks like this, and we call the term rule, which returns the right node, right? So the right node is returned by another call to the term rule. So this is in essence the implementation of the rule expression. You see that it just sequentially does what the rule suggests. Tries to evaluate the term rule, then tries to see if it's at the end, then generates the fork rule, and eventually, if I scroll down a little bit more, if we have the fork, we essentially take the fork and we say that even earlier with the fork, let me see, we say that when we construct the fork, so we already have the fork, which is constructed with the proper type right here. So the left node is already set to be the left, right? So the left hand side is already set right here. So right here we say that the left node of the fork is the left, and as we are finished with another term rule with the final part, we set the right node. So the fork has the left node and the right node, and so the right node is also set. So left is set as the left, and right is set as the right for the fork. And notice that this fork is constructed with the plus or minus type because we simply extract the character from the token stream, and it's going to be either plus or minus. So the type of the node will be plus or minus as we do this construction. So this is the actual implementation of the expression rule. Let's take a quick look at the term rule, which we already rely on. We're calling it. So the term rule is defined next. So this is another method that represents this syntax. So first is just checks whether, again, we're at the end of the input and the term rule does not match the end of input. We say that this is an error, something is wrong, and we say unexpected end of input. Okay, so I'm just going to skip this and scroll it down a little bit more. So we're looking at the term rule right here. Right, so we're looking at the term rule, and what we do here, we say, okay, we're expecting the primary to be the first part here of our input, and we call the primary rule. So not surprisingly, the primary rule returns an abstract syntax tree node, which we call left. So the first thing that is generated here successfully is the left node. So we construct this left node as step number 1. We check whether there was some errors, and if we had some errors, that we just get out of here with the error code already embedded in this node. Then again, we check for the end. Then we check whether there is multiplication or division. Right, multiplication or division. And so if you want to implement the remainder operator, of course you need to be able to add it right here on this line. This is where you'd be detecting it. So the next thing that happens, we check for these multiplication or division, and you can also add another check for the model operator, because this is not implemented in this prototype. And then we say, yes, there is something like this in place, and we immediately construct the fork, right? So the next thing that we construct here is the fork node, right? So it's called internally in this implementation the fork node, and this fork node gets its type again from this character, multiply or divide. The first character in this token, of course, will be character this asterisk that represents multiplication, or this forward slash that represents division. So we're going to get the fork. And then what we do is that as we proceed and everything seems to be working okay, then we immediately connect the fork with the left node. So we make this connection right here. So this connection happens right here as we assign left node to the left hand side of our fork. So this connection is already made. It's actually the same way we did this in expression. You will examine the code. It's very, very similar. And then we say, okay, so after multiply or divide, we're expecting another primary. And here we make a call, and if everything holds, we construct the right-hand side node. So the final step here is construct the right-hand side node, okay, like this, and eventually, of course, it gets attached to the fork right here. So we make this connection from the fork to the right-hand side node as the final step. So this is happening in the last part of this processing of these primaries. Okay, so you can again clearly see every part sequentially as it appears here inside the rules that we're trying to represent by writing Java code while constructing these nodes that capture the actual input. Right, so here, for instance, if we try to multiply 3 by 6, or something like this, we would have the multiply sign, right? And this would be our fork that represents the multiplication, and then will be 3 multiplied by 6, and every bubble here represents an object of type AST node. It's our helper class that can represent both forks and those terminal nodes with actual numbers. So let's also take a very quick look of the implementation of the primary rule. So this is yet another method that we have here. It's called primary rule. Let me see. Again, we check for an unexpected end of input. I'm just going to skip this and scroll down here. And so we begin implementation of the primary rule by naturally checking whether it's a number, right? So we say, okay, if we get the number in the input, we say, okay, this is a primary. So what we do is that we construct this primary AST node and we return it. And so this way we generate abstract syntax tree node. AST stands for abstract syntax tree, and it's a primary because it's a number. Another possibility that we have plus or minus. So we check for plus or minus right here. So this is the next step, that we check for this plus or minus right on this line. And we say that this must be a unary plus or minus. And so for this, we will construct the fork. So we construct the fork node, which will capture the unary plus or minus. Okay. So for a structure like this, what we do, for instance, is it's a unary minus, for instance, followed by the number like 5. So this is the type of tree that we generate. So when in our expression we use something like -5, right? For instance, 3 plus -5. So what's going to happen is that -5 will be interpreted by the primary as it will have to construct the fork, which will store the minus operator, which will be representing the unary minus, and it will store the 5 as the right node. Okay, it stores the right node, and the left node will be stored there as a null reference. We will know that in case of the unary minus, the left hand side is missing, only the right node is present, and so we obtain this primary, right? So the next thing is that we call primary rule, and so we obtain our primary right here. So basically this primary that should look like this is returned by call to primary rule. So this is where we execute a recursive call. The primary rule calls itself to check again whether this thing here is a primary, and this returns back the right node, which is here, over here, becomes 5, because minus was already processed. This minus was already stored in the fork node. And then the final part of the primary is to check whether we're dealing with sub-expression, which is delineated by a set of matching parentheses. So let's see. So I'll just scroll a little bit down, just a little bit more. So this is the final check that the primary rule does. And you can see that in this part, what we do is, of course, we simply check whether this opening parenthesis is present. We say, oh, this is opening parenthesis, so it must be this construct, basically parenthesized sub-expression. Right, so we say here it's a sub-expression. And what we do next is we then go right to the top and we call the expression rule. So we then say, okay, let's call the expression rule and deal with everything that that will be coming inside right here. And we're going to get our primary this way by calling the expression rule. Okay, so the primary will be represented by expression rule, and this primary, of course, this sub-expression here can be pretty complex. So right here, what comes back as a primary node could represent the entire, this could be the entire complicated structure, tree with multiple nodes and all sorts of multiplications, divisions, addition, subtraction, and everything. But it comes back as a primary because it's being parenthesized, right? So it's enclosed inside the parentheses. And then we do our final check here, right? So right here, so now we have this primary that we already constructed, and the final check here is simply to see if this closing parenthesis is present, right? So right here, we just check for this closing parenthesis, and we say, like, let's just make sure that it's present there, just to make sure that this structure looks like with the closing parentheses. And we say if it's not there, then missing a closing parentheses. Otherwise, we just return the primary from here. So this is the entire set of logic that we have here to implement the primary rule. So these are three rules that we have that implemented as Java methods, and they implement these grammar rules. So this is a very nice exercise. I know that it can be a little bit overwhelming when you look at this the first time, but it can be an interesting experience just to, at your own pace, examine the code. And I have some comments here, and you can see here and there what's happening. And the most important part then when we call the start, so in our main program, what we do, we call the start rule. So now we can go back to the Lexer start rule and see what it does once again. So the start rule, step number one, it tokenizes the input. So it basically takes whatever the input is and generates that array of tokens that we call token stream. There's actually, you can call debug print tokens, and you can see what the actual tokens are if you'd like. So this is commented out. This is for debugging purposes. Then we make sure that we set the first token to be the current token by calling the begin method, and we simply return the expression rule, which returns back the root of our tree. So when the expression is evaluated, we return AST node from our expression rule, which is some sort of abstract syntax tree that represents some sort of computation. So this can be minus 6, and this can be multiply right here, and this could be I don't know, 2 and 77, whatever, right? So it can be any number. So something like this is going to be generated by all of the rules, but what we return from the start rule, we return the root. Okay, so what is returned by the expression will be the root that we return back to the caller. And so this is what's going to be returned back to our main from the start rule. The result here is the root of our expression, and right now we're printing it. Okay, so right now all we're doing here is just printing its structure. Right now we're just printing its structure, and in our next video we'll just run a few examples just to see what kind of syntax tree is generated by our start rule and all the underlying expression term and primary rules.